Hey, there we are. Good afternoon, lads and ladies. Welcome back to MAC1140 Pre-Calculus. We are done with our section on matrices. There's a little more that I would have liked to gone into, like Kramer's rule and stuff. I think it would be wise to look at one or two problems involving determinants. So I'm going to do that today. Just solve one or two little kind of fun determinant problems for you, and then we will leave that behind entirely and begin talking about sequences and series, completely different thing. I know that the video from August 2nd still hasn't been replaced. I've been trying to upload it all morning, but I'm having trouble in YouTube. Every time I start uploading, it fails. So I'm going to keep trying through the rest of the day today, and I promise I'll get that link fixed. Just so you know, I'm aware of the issue. What else do we want to say here? Take a quick look here. Make sure everything is on the up and up. Maybe my internet connection must be shitty.
Professor?
Yes.
I sent you an email because something family related happened, and can you check your email after class?
Sure. Yeah, as much as I can. This is one of the other things I need to talk about, actually, so I'm glad you mentioned. I am not going to be able to do an office hour today. I have to go with my wife to a doctor's appointment right after class. It's at 3. But I will check my email. I think I should have some time while I'm there at the doctor's. I'll check the email and make sure to get back to you today. Alrighty. Yeah, so I would like to do one or two little kind of cute determinant problems. Today is August 4th, 2021. There are a handful of places in calculus where you will need to calculate determinants. The Jacobian matrix in Calc 3 is one of them. Another one is the Wronskian in differential equations. These are things that come up from time to time strictly within the study of calculus, and the things that come up all the time kind of in broader mathematics when you learn about eigenvalues, eigenvectors, stuff like that. In physics, it's going to be a very, very big deal there. So understanding a little bit how to calculate determinants sneakily is a big deal. So I'm going to show you a few problems with determinants. And there are a handful of determinant problems in that homework set that's up there for you. And then we're going to talk about our last topic for the semester, which is sequences and series. Sequences are hugely important in the foundation level stuff for calculus. So when we want to actually define in a rigorous way what the real numbers are, we need to talk about sequences. And then both sequences and series play a big role in Calc 2, where you study sequences kind of as an object of their own interest. And then you use them as building blocks for series and then power series, which are very, very important in Calc 2 and differential equations. So these things will be relevant throughout calculus. Sequences are sort of the most foundational of all these things, but all of this stuff is going to be fun. We should begin with some determinant problems. Some determinants. So for the first one, let's just straight up calculate the determinant of the matrix A, where A is, I'll use a 3 by 3, how about 1, 0, 2, 0, negative 1, 0, 1, 1, 0. It's a somewhat sparse matrix. We've got 4 zeros in there, which is a nice thing when it comes to calculating determinants. Remember how this works. We're going to need to pick a row or a column to expand about. And then we'll do that little thing with minors and cofactors, where you kind of cover up the row and column and take the determinant of the little guy that's left over. Can someone recommend a row or a column about which to expand? And I want you to think about which one you choose.
Is it the one with the most zeros?
Yeah, Yeah, Erica nailed it, and I think Ainsley, what you were saying there was good too. Going about the second row or the third column would be wise, because exactly like Erica said, we want to use whichever row or column has the most zeros. So if I use column 3, that's got 2 zeros. If I use row 2, that's got 2 zeros. And those are going to be my best choices here. I think in the last example we did yesterday, I calculated a determinant by expanding about the third column. So just for the sake of diversity, I'm going to expand about row 2. Remember, before you do this, you got to come in here and kind of assign these pluses and minuses in this checkerboard pattern. So you start with a plus in the top left, and then it goes plus, plus, and you keep going with that. Minus, plus, minus, plus, minus, plus. So expanding about row 2, we see that the determinant of A is equal to, I'm going to expand about the second row, it's this row. We start with this guy with his attached sign times the determinant of the little matrix you get by covering up this row and this column. So if I cover up row 2 and column 1, the little matrix that's left over is 0, 2, 1, 0. So I'll write everything out here. -0, the negative coming from the little minus there, even though it doesn't matter for this, times the determinant of the little matrix that I get covering up that row and column, which is 0, 2, 1, 0. Next, I'm moving along this row. So I'll have -1 with a little plus there. So that's going to be plus -1 times the determinant of the little matrix I get by covering up that row and that column. So now the column I need to cover is that guy's column, which is something skinnier than my finger for this. It's the second column. So that leaves me the little matrix 1, 2, 1, 0. And then finally, getting to the third guy in row 2, I would have -0 times the little determinant I get covering up row 2 and column 3, which is 1, 0, 1, 1. All right, so that's how we expand about the second row. And the same thing about any row or column. The nice thing here, we wouldn't, if I was doing this on a test, if I was trying to do this quickly myself, I wouldn't have written the first one and I wouldn't have written the last one, because it's only this one that gives me anything. The other two have those zeros attached to them. But just writing all that so you can see exactly where everything comes from. This is going to be the negative of the determinant of 1, 2, 1, 0, which is negative, bracket here, 1 times 0, minus 1 times 2. Remember, the determinant of a 2 by 2 the determinant of a little matrix A, B, C, D, a 2 by 2, is just the product of the diagonals subtracted, AD minus CB. The order there does matter. It's got to be AD minus CB, not the other way around, otherwise you get the signs wrong. So what is this? This is negative 1 times 0 minus 1 times 2. That's 0 minus 2 inside. That's negative 2, which is positive 2. And what you see is if we expanded about any other row or column, we'd get the same thing. Let me go ahead and do it about column 3. This time I won't write all the extra stuff. So if I go expanding about the third column, that's this column, the only non-zero term is going to come from this guy, right? I'd have this times the little matrix determinant minus this times the little matrix determinant plus this times the little matrix determinant. But since these two are both zeros, I know it's just going to come from that guy. So it's going to be 2 times the little determinant I get by covering up that row and that column. Oop, I got a shadow here. So that's 0, 1, sorry, 0, -1, 1, 1. So that's 2 times det 0, -1, 1, 1, which is 2 times 0 times 1 minus 1 times -1. And that's 2 times 0 minus -1, which is 2 times 1, or just 2. So yeah, same determinant either way. Certainly it should be, and it is. The only non-zero piece came from this guy. We know that both of the pieces that would come from these are going to be 0, so we don't even bother writing them. I'll just write this guy, which is 2 times the determinant of the little matrix I get when I cover up this column and this row. So that's this guy, which is what you see here. And then using my AD minus CB formula, that's 0 times 1 minus 1 times -1, 0 times 1 minus 1 times -1, which is 0 minus -1 with the 2 up front. 0 minus -1 is 0 plus 1 is 1, so that's 2 times 1, which is 2, just like we got the other way. So the determinant will never change based on how you calculate it, as long as you do it correctly. Another sort of fun question you can ask is, under what conditions will a matrix be invertible? And you can put like some variables in there. Now let me see, I don't have one of these prepared for you ahead of time, but it's something that I have put on tests in the past, and I just think they're cute problems, so I'd like to show you. Let's see if I can get one here that's not going to be gnarly. Yeah, this is fun. So last little determinant problem, last matrix problem overall. Find the values of x such that the matrix A, which is going to be, how about, choose to be that. Let's do 1, 0, x, x squared, 1, 0, and x, 0, 1. Find the values of x such that this matrix is invertible. Okay, so you plug in different numbers for x, and that's going to be different matrices. I want to know what numbers can you plug in for x such that this matrix comes out to be invertible. So kind of twofold problem here. You have to remember, what's the condition under which a matrix is invertible? Anybody remind me that?
The determinant must not be 0.
Very good. So a matrix is invertible if and only if its determinant is non-zero. So what should we do? I have here this matrix. I want to know what numbers I could plug in for X and get a invertible matrix here, I know that any matrix is invertible if and only if its determinant is different from 0. So I should find the determinant of this matrix, right? If I calculate the determinant of that matrix, I can figure out what values of X make that determinant 0, and what values of X make that determinant something other than 0. Turns out this is actually a big deal when it comes to finding eigenvalues and eigenvectors. So worth exploring a little bit. I have to pick a row or column to expand about. Seems like every column except this one has some zeros. This one has no zeros. This one has 2. This one has 1. This row has 1, 0, 1, 0, 1, 0. So I think we'll go about column 2. So if I expand about column 2, I can calculate that determinant pretty easily. It's going to be 0 times the little determinant I get when I cover up row 1 and column 2. Covers back. So if I cover up row 1 and column 2, I would get this guy. So I'd have 0 times the determinant of x squared 0, x1. Go ahead and write it out again. Let me put my plus minuses in here. So I'd have 0 times, so I guess negative 0 times the determinant of the little 2 by 2 you get when you cover this and this, which would be x squared 0, x and 1. And then plus 1 times the determinant you get when you cover up column 2 and row 2 like this. So that's 1 x 1 x x 1. And then minus 0 times the little determinant you get covering up row 2, or sorry, column 2 and row 3, which would be 1 x x squared 0. And again, I'm just writing this stuff for your benefit. You can get comfortable with how the expansion process works. Obviously, the first and last terms are 0, regardless of the little determinants, because it's being multiplied by 0. So I don't care about either of those. I just care about this guy. He's being multiplied by 1. So that's 1 times 1 minus x times x, which is 1 times 1 minus x squared. So that's the determinant of this matrix. No matter how you calculated it, you would get 1 minus x squared. Some ways it might be a little nastier looking at first, and you'd have to combine like terms, distribute, cancel. But by choosing to expand about this column, which has 2 zeros, I made my life as easy as it could possibly be. Therefore, A is invertible as long as that A is not equal to 0, that A equals 0 if and only if 1 minus x squared equals 0. Well, 1 minus x squared factors. That's 1 minus x times 1 plus x. It's a difference of squares. So det A is equal to 0 if x is equal to 1 or negative 1. So my matrix has a 0 determinant if you plug in 1 or negative 1 for x, which means as long as you don't do that, your matrix has a non-zero determinant. Finally, we conclude that the matrix A is invertible as long as X is not equal to plus or minus 1. And these, say again, are cute problems that I have an affinity for and have in the past shown up on my tests. Strong enough here? Okay. That's it on matrices. That's the whole story for matrices. We need to talk about sequences, series, summation notation. I want to sneak kind of one other thing in here if I could. Partial fractions. Tell you what, let's do the sequence and series stuff, and if there's time to come back to partial fractions on Thursday, we'll do that, because we did give ourselves that extra day. Forget where in your textbook this is. I'm going to use the same notation. So take a second to. A sequence, the things we're beginning on now, sequences and series. A sequence is really a function, but it's a special kind of function. This is 12.1. Sequences and summation notation. A sequence is a special kind of function whose domain is only the whole numbers. That's the idea. So everybody has in their mind some idea of, I think, what a sequence is, right? Like a list of numbers or something like that, like the Fibonacci sequence. Any of us have heard of this? So kind of informally, the informal definition is that a sequence is a list of numbers. So some famous sequences would include, 2, 3, 5, 7, 11, 13, 17, and so on. Or maybe 1, 2, 4, 8, 16, 32, and so on. Or maybe 3, 1, 4, 5, 9, 2, and so on. What other famous sequences you guys likely to know? 0, 1, 2, 3, 4, 8, 13, so on. All famous sequences, right? Does anybody recognize the first sequence? Someone mentioned these objects the other day, made me happy.
Prime numbers.
Yeah, this is the sequence of primes. The second sequence? Next, 64. Ooh, what was that?
Even numbers.
Certainly these are all even. They're kind of super even numbers. They're all powers of 2. In other words, each one of these can be written as 2 to the n, 2 to the 0, 2 to the 1, 2 to the 2, 2 to the 3, 2 to the 4, 2 to the 5, and so on. Anybody recognize this sequence? Next one's a 6.
Looks like pi.
Ah, these are the digits of pi. Okay, and the bottom sequence.
Fibonacci's number.
Very good. That's the Fibonacci sequence. The Fibonacci sequence and the second one there, the powers of 2, are both a part of kind of special families of sequences that we're going to study specifically. So this guy is called the What's the trick to getting the next Fibonacci number?
Add up the last one.
Yeah, you take the sum of the previous two, right? So 0 and 1 sums to 1. 1 and 1 sums to 2. 1 and 2 sums to 3. 2 and 3 sums to 5. 3 and 5 sums to 8. 5 and 8 sum to 13, and so on. A sequence like that is called a recursive sequence, and I'll define those for you in a minute. Now, this is an informal definition, right? This is like, okay, a list of numbers. But mathematicians, we like kind of formulaic things. We like things to be very rigorous, very clear, undeniable. So there is a formal definition. A sequence, and there's notation for this. We put it in curly braces. We write A sub n for the nth term of the sequence. And we like to specify kind of where it starts, like maybe the first term we call the n equals 1 term. And we like to say that they go on and on for ever and ever. A sequence is a function whose domain is just non-negative whole numbers. Maybe from 1 to infinity, maybe from 0 to infinity, depending on what we're talking about, but just the whole numbers. So for example, in this sequence of primes, I might call a sequence of primes P sub n. So the very first prime, P1, I would say that that's 2. P2, I would say that that's 3. P3, I would say that that's 5. P4, the fourth prime, is 7. P5, the fifth prime, would be 11, and so on. Or the sequence powers of 2, we're going to come back to that. The Fibonacci sequence. I might call those capital F for Fibonacci sub n. And I suppose I should be putting these in curly braces if I'm being right. Equals 1 infinity. This would be like F1 equals 0. F2 equals 1. F3 equals 1. F4 equals 2. F5 equals 3, and so on. Right, so this is the notation that we use. You can use whatever letter you want here, A, B, C, D, whatever. And then the subscript n is the input. So the idea is that this is your input, n, and the output is an. And we call A1 the first term. I know it sounds silly to say. A2 the second term. A3 is the third term, and so on. Right? That's just the terminology that we use. In general, we call A sub n the nth term. And the purpose of the bracket notation is to distinguish the sequence as the whole list, right? So when I say bracket Pn, n from 1 to infinity like this, I'm talking about the whole list of primes, the whole sequence. If I were to just write Pn itself without any of these other symbols, that would mean the nth prime, just that one guy. Okay. if I wanted to calculate the first 5 terms, I've got the first 2. I just need the next 3, F3, F4, and F5. F3, I don't know what it is, but I know it has to be following this rule. So if n is equal to 3, then Fn minus 1 is F2 plus Fn minus 2 is F1. So F3 is F2 plus F1. That's coming from the recursion relation. And now my initial conditions tell me what F2 and F1 are. This is 1 plus 0, which is 1. So F3 is 1. We already knew that because I wrote down like the first 5 or 6 terms of the Fibonacci sequence at the start of class. But this is how you would get it if I just told you the definition. If I plug in n equals 4 to that recursion relation, then it would say F4 is equal to F3 plus F2. Okay, so I need to know what F3 and F2 are. Well, F3, that's the thing I just calculated, that's 1. And F2, that was a part of my initial conditions, that's 1 also. So this is 1 plus 1, which is 2. And then finally, plugging in n equals 5 to my recurrence relation, I see that F5 has to be F4 plus F3. F4 is 2, F3 is 1, so this has to be 2 plus 1, which is 3. So the first 5 terms are 0, 1, 1, 2, 3. I know that this might seem like a lot of formality for something as simple as just add up the last 2 guys, but there's the whole universe of recursive sequences are actually very important. I spent a lot of time with my differential equations class today talking about recursive sequences because they're used to sort out power series for solutions to differential equations. They're also fun in their own right. There's another very important sequence that can be defined recursively that I want to share with you before we move on. Are there any questions about how I found these terms? Okay. This next one has a name, but I'm not going to tell you what it is right away. I'm going to use the symbol F again. I'll say calculate the first 5 terms for the recursive sequence of the recursive sequence. We use a little f for this guy, little f sub n. I'll say he starts at 0, goes to infinity, defined by the following recurrence relation and initial conditions. I'm going to say that f sub n plus 1 is equal to n plus 1 times f sub n. That's my recurrence relation. And the initial condition here is just going to be that f0 is 1. Here's the recurrence relation. And here's the initial condition. The number of initial conditions you need depends on the sort of depth of your recurrence relation. Here, this recurrence relation connects the next guy just to the previous guy. The Fibonacci recurrence relation connected a given guy to the previous guy and the guy before. So that would be called an order 2 recurrence relation, and he needed 2 initial conditions. This, since from Fn to Fn plus 1, that's only the next term, it's an order 1 recurrence relation. And that's why we can get away with just 1 initial condition. All right, same deal, first 5 terms. I might go a little bit beyond that, we'll see. But can anybody help me find F1? What should I do to calculate F1?
Just plug in 1 into the Fn plus 1.
Yeah, very good. So I'm going to plug in n equals, actually, I'm going to plug in n equals 0, right? Because if I plug in n equals 0, this gives me F sub 1, 0 plus 1. So,
Oh, okay.
no, but you're exactly right that we want to plug into the recurrence relation. And then I'll get 0 plus 1 times F0. Well, 0 plus 1 is 1, so this is 1 times F0. F0 is 1, so this is 1 times 1, which is 1. Now, if I plug in n equals 1, I'll get on the left-hand side f sub 1 plus 1, which is f sub 2 equals. And here again is 1, so it's going to be 1 plus 1 times f sub n, which is f sub 1. So that's 2 times f sub 1. F sub 1 is 1, so that's 2 times 1, which is 2. Next, I would plug in n equals 2, and that will give me f3 on the left, and then I'll have 2 plus 1 times f2, which is 3 times f2, which is 3 times 2, or 6. Then we plug in n equals 3, and I get f4 equals 3 plus 1 times f3, which is 4 times f3, which is 4 times 6, or 24. And I'll do one more. We've already got the first 5 here, right? 0, 1, 2, 3, and 4. Those are 5 terms. But I'll do one more. If I plug in n equals 4, then I get f sub 5, which is, according to the recurrence relation, 4 plus 1 times f sub 4. So it's 5 times f sub 4, which is 5 times 24, which is 120. So the first few terms of the sequence are 1, 1, 2, 6, 24, 120. I'll tell you the next one is 720. Does anybody know this sequence? Has anybody taken statistics in high school or elsewhere? Oh my goodness, I've got a class of virgins. This is exciting. This is called the factorial sequence. And if you want to, you realize that here, for example, at this stage, I could have written this as just 2 times 1, right? I could have written this as 3 times 2 times 1, because f2 is 2 times 1. I could have written this as 4 times 3 times 2 times 1. I could have written this as 5 times 4 times 3 times 2 times 1. So the sequence here has a name. It's called the factorial sequence. And the normal notation for this is instead of writing f sub n, we write n and then an exclamation mark. And there is a general formula. Finding a general formula for the Fibonacci sequence, by the way, can be done, but it's a little bit hard. But here, what we found is kind of a general formula. We found that the 5th factorial is 5 times 4 times 3 times 2 times 1. The 4th factorial is 4 times 3 times 2 times 1. The 3rd factorial is 3 times 2 times 1. The 2nd factorial is 2 times 1. So this is usually defined as n factorial equals n times n minus 1 times n minus 2 all the way down to you get to 3 times 2 times 1. this thing is going to play a very big role in your Calc 2 class. Shows up a lot. All right, so that's recursive sequences. They're sequences where the next term is given as a combination of the previous terms. The other way of defining this is as we did by saying n plus 1 factorial is equal to n plus 1 times n factorial together with the initial condition that 0 factorial is equal to 1. A lot of people really don't like this definition that 0 factorial is 1. It just bugs them. Somehow that bugs them, but this doesn't. It's just different notation. But this is also, in addition to being very important in Calc 2, when you talk about power series, the factorial sequence is most famous in combinatorics as the accounting thing. So if I want to know how many ways I can arrange n people in a circle, that's always n minus 1 factorial. It shows up in the choose function. If you've ever seen that, or you talk about permutations, shows up a lot there as well. Anyway, the other two important types of sequences we need to discuss are arithmetic and geometric. Arithmetic sequences are kind of boring, so I'm going to hit them real quick. These are the sequence version of a linear function. But there's a way of thinking about it kind of in terms of the language of sequences, but that's all. They're just linear functions. For example, if I take the sequence an, n from 1 to infinity, with first few terms, to be like 5, and then 9, and then 13, and then 17, and then 21, and so on. What do you notice about this sequence? What do you notice about consecutive terms in this sequence? How do I go from 5 to 9?
They are up by 4.
Yeah, you add 4. And then to go from 9 to 13, you add 4. To go from 13 to 17, you add 4. To go from 17 to 21, you add 4. So you can tell me what the next term of the sequence is, no problem, right? 25. What about finding a formula? Remember, we want to start at n equals 1. So it might be helpful for me to write these like we did last time. We had to do this 9, 13, 17. I
Would
know
it just be n plus 4?
not quite. So there has to be a 4n in here, right? Because each time we go from one to the next, we're adding 4. So here's what I would say. I would say 5 is 1 plus 4 times 1. 9 is 1 plus 4 times 2. 13 is 1 plus 4 times 3. 17 is 1 plus 4 times 4. So an here is 1 plus 4 times n. So that would be your formula for the nth term. And arithmetic sequences always have a formula that looks like this: some constant plus some other constant times n. Now, more generally, the formal definition an arithmetic sequence is one in which we add a fixed constant to get from one term to the next. That constant is called the common difference. So in the example above here, the common difference is 4. And I'll let you think about how you would come up with a generic formula for any arithmetic sequence. I'll tell you, it's actually nicer if you let n start at 0. If you let n start at 0, it's always going to be this plus the common difference times n. You can play with it a little bit. There's nothing too deep there. I don't have anything else to say about arithmetic sequences. They're boring. But there's another family of sequences that is not boring, which we're going to talk about before we talk about summation. And that is geometric sequences. Geometric sequences, these are the sequence version of exponential functions. For example, we saw one earlier. 1, 2, 4, 8, 16, 32, and so on. Before I called these powers of 2, and they are. But you'll notice that to go from one to the next, you multiply by 2. So the term geometric comes from that sort of behavior. Just like arithmetic are sequences where you always add some constant. Geometric sequences are a sequence where you always multiply by some constant. And that's the formal definition of a geometric sequence. Before I write that down, I just want to observe that here, I could write an equals 2 to the n, as long as n starts at 0. Formally. So right, this looks like an exponential function. 2 to the x is an exponential function. 2 to the n is an exponential function too. But we call them geometric sequences because of this repeating behavior. So formally, a sequence, and I am going to write this as formally starting at 0, n equals 0 to infinity, is called geometric if to go from one term to the next, we multiply by a fixed constant. And that fixed constant has a special name too, just like the constant from arithmetic sequences was called the common difference. This is called the common ratio. And we usually use the symbol R. We're actually going to talk more about sequences, series, and geometric sequences are going to play an important role in that. So I do want to show you the sort of general formula for a geometric sequence here, and say a little bit more about that. So I will look at a couple other examples. So yeah, how about another example? Find the common ratio and a formula for the sequence AN, where n starts at 0, goes off to infinity. Those first few terms are, let's be somewhat gentle about the now we're going to go whole 5, and then negative 10 thirds, and then positive 20 ninths, and then negative 40 27, and then positive 80 firsts, and so on. Right? So by telling you to find the common ratio, I'm implying that this is a geometric sequence. Right? Sequences with common ratios are geometric. So, can anybody help me find the common ratio for this geometric sequence? Is there a constant that you multiply by, same constant, to go from one term to the next here?
2/3.
Very close, very close. 2/3 is certainly a part of it, but there's a little more to it.
Negative 2/3.
Beautiful. Negative 2/3, right? To go from 5 to negative 10/3, you multiply by negative 2/3. If you multiply negative 10/3 by negative 2/3, you get positive 20/3. And again, 20 times negative 2 is negative 40, 9 times 3 is 27. Again. So my common ratio is negative 2/3. This is one place where geometric sequences are kind of different than exponential functions, right? With exponential functions, the base had to be positive because we were worried what's going to happen if you plug in fractions or weird numbers. But with a sequence, I'm only ever plugging in non-negative whole numbers for n, for my variable. So I can have the base, aka common ratio, be a negative number without any problems. All right, who's going to help me find a formula for the nth term? Up here, this guy whose common ratio was 2 was just 2 to the n. This guy whose common ratio is negative 2/3 should probably involve negative 2/3 to the n, because like here I've multiplied something by negative 2/3. Here I've multiplied something by negative 2/3 twice, so that's negative 2/3 squared. Here I've multiplied by another negative 2/3, so that's negative 2/3 cubed. Another negative 2/3, that's negative 2/3 to the 4. the thing that goes in front here is the 5. Try it. 5 times negative 2/3 to the 0 is just 5 times 1. It's 5. 5 times negative 2/3 to the 1 is 5 times negative 2/3, negative 10/3. So this guy is A0, this is A1, this is A2, this is A3, and so on. There's something special to say about geometric sequences. I'm going to share that with you in just a second. But the general formula for a geometric sequence AN, whose index starts at 0 and goes to infinity with common ratio R and starting term, say A, is AN equals A times R to the N. I used to write A0 down here, and you can do that too. Starting term A0 times R to the N. I don't want to scare you with extra notation, so if you want to leave the 0 off, you can. But it all matches up very nicely. This is assuming that you're starting at n equals 0. If you start at n equals 1, then this would shift to an n minus 1. Your textbook unfortunately does that. I don't know why. It's a really bad choice of notation in both cases, arithmetic and geometric. All right. Geometric sequences have a neat property. To discuss that, first I want to plot this for you. I'm going to use Desmos. I don't think Desmos accepts sequence notation. If I ask if a sub n equals 5 times negative 2/3 to the n, we'll see what it does. Oh, it's trying. It's trying. I don't know how to tell it to restrict to just the whole numbers, though. So instead, how can I do this? Desmos. Yeah, I could use floor function. Use the integer part of x. All right, you're not going to like this notation wise here, but we'll take floor n. Yeah. But then it's still just going to do this. All right. We'll try. So the graph of this function, the graph of this sequence, imagine they're just dots rather than here. Sequence. I think this will probably work. So I'm going to set it up ahead of time. I just got to plug in our sequence. Okay. Don't pay too much attention to any of that. Plug in our sequence down here, which is 5 times negative 2/3. Use the variable x because we got to. That accepts either. All right, and then we're going to rescale the y-axis. So negative 1 to 1, and then just 12.5. Right. So what you see here is that the first few terms of the sequence are like, we've started with the 5 way back at 0, and then they bounce back and forth, but very quickly they get close to 0. So the graph of the sequence we just looked at kind of looks like that -1 to the n over n plus 1 sequence. It goes very, very quickly towards 0. A fun fact. If the absolute value of r is strictly smaller than 1, then as n gets bigger and bigger, r to the n gets closer and closer to 0. The example we just had up is a little bit rough to look at. So for example, let's look at an equals 1/2 to the n. On the one hand, you can think about this as coming from 1/2 to the x, right? Which is an exponential function you guys know well. It's got a horizontal asymptote on the right, which is y equals 0. On the other hand, you can just think of the terms of the sequence. A0 is 1, A1 is 1/2, A2 is 1/4, A3 is 1/8, A4 is 1/16, A5 is 1/32. You see, the top is always 1, and the bottom is getting much, 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 much bigger. In fact, each one is half as big as the last. So the graph of this sequence I mark this way up here as 1, then we start at the point 0, 1, and then we go to the point 0, 1/2, then we go to the point, 1, 1/2, then we go to the point 2, 1/4, and then the point 3, 1/8, and then halfway. All right, you see very, very quickly, this is getting closer and closer to 0. These y values, these outputs get close to 0 very quickly. And sort of formally, the way we would write this is as n goes to infinity, 1/2 to the n goes to 0. And there's nothing special about 1/2 besides it having an absolute value that's less than 1. If you do this with 1/3 or 2/3 or 3/5 or -pi/15, they'll all do that. So more generally, if the absolute value of r is less than 1, then as n goes to infinity, r to the n will quite quickly go to 0. And I wanted to leave with this fact because we are going to use that when we talk about series and summation notation, which is what we're going to do on Thursday. All right, so tomorrow, it's our last day of class. Congratulations, we're there. I'm going to teach you about this scary new thing called sigma notation. People tend to not like it at first, but I promise you it's big, so it's going to be important. Tomorrow, we're going to learn about sigma summation notation. I am going to publish one more short homework set. Maybe I'll just put the stuff in the study in the quiz for the final. I'll either, yeah, probably just in the quiz for the final. So I'm going to tell you what, short homework, little homework on sequences and series. And then I'll put up a quiz to kind of help you review for the final. And those will be the last few things you need to do before the final exam, besides the take-home test, which I'll give out on Thursday after class tomorrow. All right, so in class tomorrow, we're going to learn some summation notation. Today, I will publish your sequences and series homework. It'll be short, I promise. Then you'll have one more quiz, and the final will be on Monday. So the next few days quite busy. Make sure you are finishing up the homework on systems of equations. And yeah, that's it. Again, doctor's appointment today, so I got to run to that like right now. Not going to have my normal office hour this afternoon, but if you need to talk, send me an email. Ainsley, I got you. I know you said you emailed me. I'll take a look at that on the road or as soon as I safely can. And we'll go forward from there, guys. Okay, if you're concerned about anything, please reach out to me. Let me know. You can come by my office hour tomorrow or send me a Canvas message today. Work hard on the homework and take good care of yourselves.